Hello everyone. Welcome to second lecture on errors in numerical calculations. In the previous session, we have discussed about the definitions of exact number, approximate number, and the errors involved in approximation, the types of errors, and we have solved a couple of examples at the end. Today, we shall discuss two important concepts, namely estimation of error in the evaluation of a function, and we shall also study estimation of the error in approximating a given function with the help of Taylor series. So let us begin with the first topic, that is estimation of error in a function. So let us consider the function f. It is denoted by the symbol capital X. So capital X is a function of x1, x2, xn. That is, it is a function of n number of variables. So the variables are particularly x1, x2, xn. So these are the independent variables, whereas capital X is a function of these independent variables. Now, when there is involved an error delta x in capital X, delta x is a error which is involved in capital X due to the errors in the independent variables. So independent variables are x1, x2, xn, and due to the errors in x1, x2, xn, namely delta x1, delta x2, delta xn, respectively in the variables x1, x2, xn. So what happens? There will be an error existing in the original function capital X. So I hope you understood. Since capital X is a function of x1, x2, xn, if there is an error involved in the independent variables x1, x2, xn, namely delta x1, delta x2, delta xn respectively, then there will be an error involved in the function capital X, and it is denoted by delta capital X. Now, if you are given with this error in the function delta x, you can calculate the errors involved in each individual functions, and vice versa. If errors involved in each individual functions is given, you can compute delta x. So there are formulae, like you can observe here. Delta x1 is the formula. This is the formula which is giving you the value of delta x1. So delta x1 is the error involved in the first independent variable x1, and it is given as the total error involved in the function capital X divided by number of independent variables. How many independent variables are here? N number of independent variables are there. So number of independent variables multiplied by partial derivative of this capital X with respect to the first independent variable whose error we are estimating. So that we have to take in the denominator. So this formula gives us the error involved in the first variable, that is x1. Similarly, we can compute the error involved in delta that is delta x2 in the second independent variable x2, and in the same way, this is the general formula for finding the error involved in evaluation of the nth independent variable xn, and it is denoted by delta xn. So this is the formula. You can observe everywhere delta x, that is the error involved in the function, is given in the numerator divided by number of independent variables into partial derivative of the function with respect to that independent variable whose error we are estimating. So this is the thing we have to keep in our mind, and with this background we can look at an example. You can solve this example quickly. You please observe what is the question. The error in the measurement of the area of a cross section of a rod. See, the rod is we can assume that the rod is a circular rod. Okay, usually the rods will be circular in nature unless otherwise specified. We can take the rod to be circular. If the rod is circular, cylindrical, then its cross section will be a circle. Its cross section will be a circle. See, its cross section will be like a circle. If you cut the rod, it will have the cross section like a circle. Now, if the error involved in the measurement of its total area is given to be 0.2%. See, whenever the percent is mentioned, you should understand that it is the percentage error. So percentage error given is 0.2. It is the percentage error in the evaluation of the area of a cross section of a rod. Now you can look at the question. What is the question? What we have to do? We have to evaluate how accurately should diameter be measured. So we have to determine the error involved in the diameter of this circular rod. You look at the formula for area of a cross-sectional area of a rod. Cross-sectional area, we have said it is to be circular, and we know that area of cross-section, that is area of a circle, is pi r square. Pi r square is the formula for area of a circle. R is always half of the diameter. If d is the diameter, R is half of the diameter, and in place of R, if you substitute d by 2, it will be pi d to the power of 2 by 2 to the power of 2, that is 4. So area of cross section is pi d square by 4. Now what is given? The percentage error in A is 0.2 they have given. If it is written as percentage error, no need of writing percentage. If it is written as only error, then 0.2% we have to write. That percent indicates that the error is percentage error. We are writing here percentage error in A, that is 0.2. Now what is the definition of percentage error? It is relative error. That is a delta A divided by A, that is the relative error, multiplied by 100. RHS as it is. Now keep delta A as it is on left hand side. Cross multiply this A, it comes to the numerator. Cross multiply 100, it comes to the denominator. So 0.2 divided by 100 is 0.002. Two zeros are entered here. Now 0.002 into area formula we have just now seen. Area formula, it is here. You can observe. Area formula is pi d square by 4. So that we are substituting here. That is pi d square by 4. Now since A is a function of only one independent variable, you see area A in the formula, if you see, area is defined as pi, which is constant, 4 is constant, d square. So how many independent variables are there? A is a function of only one independent variable, d. Therefore, because of this, what can we write? Error involved. See, error involved in A, that the function is given to be this. Then we can evaluate the error involved in D. That is, you have the formula. Error involved in the first independent variable delta x1 is equal to error involved in the total function divided by number of independent variables into partial derivative of the function with respect to that variable x1. Similarly, here x1 is d. So delta d, that is error in d, is the function here is a, that is area. Delta a divided by number of independent variables, just now we have said it is 1, into partial derivative of a with respect to d. So this is the formula we are using for delta d. In this formula, let us substitute delta a from here. So if you substitute delta a value like this, now at the same time, what is dou a by dou t, that we have to evaluate. See, dou a by dou t is nothing but we have to evaluate what is that. So a formula is here. If you differentiate this with respect to d, pi by 4 is a constant as it is. D square derivative with respect to d is 2d. So you are evaluating here. It is 4 cancelled, 2 coming in the denominator. So it is pi d divided by 4. Dou a by dou t, because a is this thing, partial derivative of this with respect to d is pi d by 2. Let us substitute it here, and you look at the formula. Delta delta A is this much divided by dou A by dou T. That is what we are substituting. Numerator divided by the denominator, that 1 divided by pi d by 2, that this value we have substituted. Now simplification, d cancelled, 2 2's are cancelled, and 1 more 2, that is cancelled totally. See, this denominator of denominator goes to the numerator, and this 4 cancels with this 4, 0.001 remains. Pi cancels with this pi, and d cancels with this d, only d is remaining. Now you take this d to the left hand side, it comes to the denominator. Pi d by d is equal to 0.001. So this is the relative error. You multiply this with 100, you will get percentage error. So percentage error in d is relative error into 100. So this much into 100, it is 2 zeros are to be omitted. So 0.01 is the percentage error in d. So we can conclude that the diameter is measured to an accuracy of 0.1%. So 0.1% accuracy will be there in the measurement of diameter if the area, cross-sectional area of a rod is measured to the accuracy of 0.2%. So this is the solution. 0.1% is the answer for our question. Now let us go for another example. Two sides and an included angle of a triangular park. See, there is a park whose shape is triangle. It is a triangular park. It's two sides and one angle. See, these two sides, and the included angle means the angle between those two sides. That is given approximately 96 feet, 87 feet, and the included angle is 36 degrees. So this much is the given data. Find the allowable errors in these quantities in order that the area of the park may be determined to the nearest square root. So you have to evaluate the errors involved in these values, that is the side B, the side C, and the angle, this angle BAC, that we have to measure if the area of a park is determined to be the nearest square foot. So now you look at the hint which I have given to you. Alpha be the area of the triangle. Area of a triangle is when two sides and an angle is given and an included angle is given. Area of a triangle is given by 1 by 2 BC sine of that angle A. So using this formula, we have to calculate the errors involved in B, C, and A. And this example is very much similar to the previous example. Please refer the previous example and try to solve this example by yourself. This is an assignment question to you. Now, let us go for the second very important topic, that is the truncation error in Taylor series expansion or Taylor series approximation of a function. See, the Taylor series expansion of a function f of x about the point x equal to a is given by this formula. This is the formula, very important formula in mathematics, that is the Taylor series expansion of a function f of x about the point a. In this, actually the Taylor series expansion is an infinite series expansion. See, the series will contain infinitely many number of terms, but for computational purpose we limit the number of terms. So considering only first few terms of a infinite series is called as truncation of the series. So while doing so, there is some error involved, and that error is called as truncation error. That error is called as truncation error. So what is the truncation error when we truncate the Taylor series expansion up to a certain first few number of terms? That we shall discuss now. Here, see this last term Rn, you can observe the series expansion. The first term is f of a, the second term is x minus a to the power of 1. See, actually here x minus a to the power of 0, here it is x minus a to the power of 1, Here it is x minus a to the power of 2. Here it is x minus a to the power of n minus 1. And in the denominator, here it is 1 factorial, here it is 2 factorial, here it is n factorial. Whatever is the power, that much factorial is there in the denominator. And here it is first 0th order derivative. That is nothing but the function value itself. Here the first order derivative, the second order derivative, the n minus 1th order derivative for this term. And the last term is denoted as Rn of x. So what this Rn of x actually is? This is the remainder term, that is after n terms. See how many terms are here up to here. It is n minus 1th degree term, but number of terms is totally n terms, because this term is having x minus a to the power of 0. So 0, 1, 2 and n minus 1. That is nothing but up to n terms. These are n terms, and after that the n plus 1th term is the remainder term. So remainder after n terms is denoted as Rn. It is actually, it's very much similar to this x minus a to the power of, it should be n divided by n factorial into, here it was n minus 1th derivative, here it should be nth derivative, and at any point, at a point, it is not actually at the point A, it is at a point xi which is in between a and x, any point which is in between a and x. So that is the remainder term, and we don't bother about this for the calculation purpose. You see how the calculation is done. You look at what is the truncation error occurred in the series approximation. If xi and xi plus 1 are two successive values of x. See, in the previous definition of Taylor series expansion, we have taken the point A, which is a neighboring point of x. So instead of x and a, we can consider xi and xi plus 1. So x is replaced by xi, a is replaced by xi, and x is replaced by its neighboring point xi plus 1. So f of xi plus 1, this is just like x, this is just like a. So x minus a, that is nothing but xi plus 1 minus xi. Into wherever a is there, we have substituted a in the previous formula. Wherever a is there, we have substituted xi, and wherever x is there, we have substituted xi plus 1. So xi is the neighboring point of xi. So up to here, you see, this is the 0th order term, this is the first order term, this is the nth order term. We have not stopped at n minus 1, we have come up to nth degree term, that is n plus 1th term, and after that the remainder after n plus 1 terms, that is Rn plus 1, which is given by this as per the previous definition. Now this term is the remainder term, and it tends to 0 when we consider this remainder tends to 0 when n tends to infinity. You see, in the denominator we are having n, so n becomes infinity, means this total value becomes 0. So that is what it is indicating. Thus, if xi plus 1 is approximated by the first n plus 1 terms, n plus 1 terms are nothing but these many terms. So this is the 0th degree term, first degree term, nth degree term. Totally how many terms? N plus 1 terms. So totally n plus 1 terms, if we consider, that is nothing but if we consider only n plus 1 terms in the Taylor series expansion. I have just now told you that there will be infinitely many number of terms in the Taylor series expansion. Out of them, we consider only first n plus 1 terms. While that means we are truncating the series. Up to here. By truncating the series up to here, there will be an error involved, and that is truncation error. And what is that truncation error? We shall see now. Now, this type of approximation, considering only n plus 1 number of terms, is called as nth order approximation. You see why it is nth order approximation, because it is having nth degree term, therefore it is nth order approximation. Now if you consider only one term, that is 0th order approximation, because the term x, this bracket to the power of 0 will be here, so therefore that is 0th order. If you consider only one term, that is 0th order approximation. If you consider two terms, that is first order approximation. If you consider n, the term of degree n, then that will be n plus 1, that will be nth order approximation. Totally n plus 1 number of terms will be there, but order of approximation will be nth order approximation. Now, how to evaluate? See what it is being told here. If this is done, that is approximated by n plus 1 number of terms, then the maximum error committed by using this approximation is given by the remainder. So this remainder will give us This remainder will give us the error involved in approximating the Taylor series expansion by considering only n plus 1 number of terms in the beginning. Similarly, conversely, we can say that if the accuracy required is specified, then it would be possible to find the number of terms that is n, such that the infinite series yields required accuracy. So the infinite series, which is being truncated to be a finite series with n terms, that can be determined. How many number of terms are to be retained, that can be easily judged by knowing the accuracy required by the that is if the that remainder is given. So then what to derive the formula for that, let us now define an interval length. Interval length is nothing but xi plus 1 minus xi, that is equal to h if it is given. Then see, xi minus 1 equal to xi. In the formula xi plus 1 minus xi plus 1 minus xi. In these places you can replace it by h. So what happens? h square h to the power of n, and here it is h to the power of n plus 1. So every other terms are kept as they are. Now here are this O of h to the power of n plus 1, why we have written, you please observe, this is the term which is having h to the power of n divided by, sorry, it should be n plus 1. Please make a correction. This bracket is h to the power of n plus 1 divided by n plus 1 factorial. So this term is having the order of n plus 1. So that is why we end our series with the notation O of h to the power of n plus 1. It means that the truncation error in the is the order of h to the power of n plus 1. You will come to know the value of h. Its power n plus 1 will be the truncation error involved in the approximation of a function with the help of the Taylor series. Now let us consider the series after the first approximation. See, it contains first approximation, first term. See, the series, the Taylor series is truncated by considering only first term. See, this term is not being considered. It is the remainder after the first term. So the first term, if you consider, that is the zeroth order approximation. N is 0 here. And which means that, see what it means. If you make the interval half, that is halving the interval length h will also halve the error in the approximate solution, because it is of order h to the power of 1. If h is 1 by 2, then the error in the approximate solution will also be of the order of 1 by 2. Whereas you look at this particular situation, which is the first order approximation. First order approximation is nothing but h to the power of 1 we have to consider. That is, 2 terms should be considered. So after 2 terms, what is the order of the remainder? Remainder is of the order of h square. So h here is square. Order of the error is h square. So if h is 1 by 2, the error in the approximation will be 1 by 2 to the power of 2, that is 1 by 4, which means that halving the interval length h will quarter. That means you will get a quarter of the error in the approximation of that particular function by choosing only first 2 term. That is, if you consider only 2 terms, that gives that yields the error of the order of h square. We say that the approximation has the second order convergence. If this is the thing, we say that the approximation. What is approximation? This is the approximation considering only 2 terms in the Taylor series series. Taylor series will be infinite series. By considering only 2 terms, that means we are doing some approximation. And this approximation, we say that it has a second order convergence because the error involved is of the order of h square. Now, let us consider an example to understand this concept very well. See, the function is x cube minus 3x square plus 5x minus 10. Now we have to determine the truncation error committed in the Taylor series approximation of the orders, Taylor series expansions of the order 0 to 3. That is nothing but we have to consider the Taylor series expansion containing only 1 term, 2 terms, 3 terms, and then 4 terms. So totally we have to calculate the error committed upon approximating the Taylor series to the orders of 0 to 4 for particularly the computation of f at 1. See, this 1 is the point at which we are expanding the function in a Taylor series, and we have to consider one neighboring point. So neighboring point of 1 can be conveniently chosen to be 0. This is our guess. This is our choice. We do this choice. We choose this value based on our data. See, this will be given. The point at which the Taylor series is required is 1, that is given. By looking at this, we can choose the point xi, that is to be 0 conveniently. And if you do so, h is xi plus 1 minus xi, that is 0, 1 minus 0, 1. So h value here is 1. And it is given that, and it can be very easily observed that f of 1 will be in the function f of x. This is the function f of x in this expression. If you, this is the polynomial function. In this polynomial function, if you put x equal to 1, you will be having 1 minus 3 into 1 plus 5 into 1 minus 10. The answer is minus 7. So f of 1 is minus 7, h value is 1, and we have Taylor series expansion of the function to be like this. I will show you. This is the Taylor series expansion containing third degree, up to the third degree term, because we have to take the Taylor series approximation of the order 0, 1, 2 and 3. So we can be quite comfortable if we consider only this term as the last term. Now here you observe the value of f at 0, the value of f dash at 0, the value of f double dash at 0, the value of f triple dash at 0 are to be calculated. In order to compute those values, let us see. F value we have in the question itself, they have given f to be this one. You differentiate this, you will get f dash. Second order derivative also obtained in the same way. So f dash is 3x square minus 6x plus 5u. Its derivative will be f double dash of x, that is 6x minus 6. Its derivative will be f triple dash of x, that will be simply 6. So f fourth order derivative of x and all other higher order derivatives are zeros, because this is the constant. After this, all other higher order derivatives will be zeros. So the function will not be that the Taylor series will not have any term after the third degree term. Third degree term will be a constant term 6, and after that all other higher order derivatives are going to be 0. Therefore we have to consider Taylor series up to the term of degree 3, that is third order term. Now what is the value f dash at xi? Xi means 0. F dash of 0, here you substitute 0 in place of x, so answer is 5u. Similarly, f double dash of 0, f triple dash of 0 are evaluated. And what is f of 0? The function is given here in the question. F is this thing, you substitute 0, that we have seen. F of 0 is minus 10. F of 0 is minus 10. Then the Taylor series is given by. So what is the Taylor series? This is the formula just now I have shown you. In this you substitute all the values, and you will come to know what is the Taylor series. Now we have the different questions. See, the first one is zeroth order approximation. Zeroth order is nothing but considering only the first term. So f of xi plus 1 minus f of xi plus the error involved will be the order of h. Just now I have told you it will be the order of h. So this is here. Now you substitute f of xi plus 1, that is f of 1 plus f of 0 plus order of h. So f of 0 is minus 10, order of h as it is, so it is minus 10. Order of h is 1, because we have seen h is 1. You please observe, h is 1. Therefore order of 1, there is no need of writing, only this is minus 10. So f of 1, the error involved will be, see, order of h, we have the question f of 1 here. F of 1 is minus 7, we have calculated in the beginning, and this is minus 10. You take this minus 10 to this side, it is minus 7 plus 10, that will be order of h. Order of h is nothing but the error involved in the approximation of the Taylor series with the help of only one term. So it is minus 7 plus 10, it is 3 units. So this is our answer. the Taylor series expansion when considered only one term in it, then the error will be of 3 units. The error will be quite significant. Now you consider the first approximation, first order approximation. So first order approximation is nothing but considering two terms, that is h to the power of one term. So there will be two terms involved in the Taylor series. After that, the error term is coming here. This is the error term. Now you please calculate this. F of xi plus 1 is nothing but f of 1. F of xi is 0. H is 1. F dash of xi is nothing but f dash of 0. So order of h square keep as it is. This gives us the error. So f of 1 is minus 7. This I have to write here minus 7. Minus 10 is the value for this. And what is f dash of 0? That is 5. 5 into 1 is 5 plus this as it is. So minus 5, minus 10 plus 5 is minus 5. You take this minus 5 to this side, it becomes plus 5. So value here is f of 1 value is minus 7. And this minus 5 to the left hand side is plus 5. Minus 7 plus 5, that will be the value of this quantity, which is the truncation error in the approximation of a Taylor series with two terms, that is of order h square, that is second degree approximation. So its value is minus 2. Now error is minus 2. Now you look at the Taylor series expansion of second order. That means it is containing 1, 2, 3 terms, h square term, order of h square. Now errors will be of degree h cube. Now we have to calculate what is this error. So this error is calculated by substituting these values. So all the values are known. If you do this simplification, answer is minus 8. Minus 8, you take this minus 8 to this side. So it becomes f of 1, whose value is minus 7. In the beginning itself we have evaluated it. This is plus 8, minus 7 plus 8. The answer is 1 unit. You see the error is decreasing in its magnitude as we are considering more and more number of terms in the Taylor series. Finally, you look at the Taylor series expansion with the term of degree 3. This is called third order Taylor series. So it is containing 4 number of terms in total, and the degree of the term, the last term, is h cube. So in this, you substitute all the values known, you will be ending with the answer minus 7 here, and this minus 7 is transferred to this, it is plus 7, but f of 1 is minus 7 and this is coming here minus 7. So plus 7 plus 7 is going to be 0. So the error involved in this approximation, that is third approximation, is 0, because the value computed by using Taylor series expansion as well as the value computed by the function, both are same. It is also minus 7, the earlier also minus 7. So there is no truncation error involved at all in the calculation of this particular third order Taylor series approximation of a function. It is noted that if the given function is a polynomial function of degree n, then its nth order Taylor series approximation gives the exact results. See, when the error becomes 0, it gives the exact value. The approximate value is same as exact value. When the degree of the polynomial is n, then the nth order Taylor series gives us the exact value. Now, this is the second question. You can very easily understand this. The function here is sin x. Its derivatives will be cos x minus sin x. Repeatedly, sin derivative is cos derivative is sin, and similarly it goes on like that. So we have to construct the series approximation of the orders up to 7. See, that is very simple work. I will show you at the point pi by 3, that is nothing but 60 degree, and find their absolute error. Very simple work I will show you. See, the function value at pi by 3 is sin of pi by 3. Sin 60 is this much. You can calculate it using your calculator. This is the exact value. So now you take this value to be xi plus 1, and we have to choose one neighboring point of this, that is to be designated as xi, and that we have to choose some value of our convenience. If it is 60 degree, 30 degree will be convenient to us, because sin 30, cos 30, that we know very well. So this is pi by 6 we have taken for xi, that is chosen conveniently. Now h will be xi plus 1 minus xi. The difference of pi by 3 minus, that is pi by 6, is pi by 6. Taylor series expansion up to 7th order term. See, 0th order, 1st order, 2nd order, and this is the 7th order term. Very long Taylor series expansion we have written, plus the order of h to the power of 8. This is the remainder after 8 number of terms. These are 8 number of terms in total. It is 7th degree term, but there are totally 8 number of terms here. And this is the error. This term is going to give us the error after 7th order approximation. Now you please see, we will substitute the values. This is xi plus 1, this is xi, this is xi, this is xi, and this is h, this is also x minus, this is f dash of xi, this is f double dash of x, this is f dash of xi, f double dash of xi, f triple dash of xi, and so on and so forth. So this is the thing which you are getting after substituting the values of all these quantities here. And when you simplify this and consider desired number of terms, see, we know the value of sine pi by 3, sine pi by 6, cos pi by 6, and all those we substitute here, root 3 by 2, and those values we will substitute, and this is the resulting expression. In this expression we consider only first term, that gives us the 0th order approximation. So sine pi by 3 is the 0th order approximation, sine pi by 3 equal to the first term, that is 0th order approximation, and this is this much. Now the absolute error, you know the value of this, exact value of this we have written already. Sine pi by 3 value we have written, sine pi by 3 is this much, this minus 0.5, that is going to give us the error involved in the first approximation. So its value is known, you take it to this side, so subtraction, that gives 0.36, and so on. This is the absolute error in the 0th order approximation. Similarly, the first order approximation, consider the first and second terms in the above series 1. This is most important. Here you consider these two terms. In these two terms you substitute this value, you know value of this, and you simplify this left right hand side with the help of calculator, take it to this side, it gives you absolute error in the first order approximation of a Taylor series. Similarly, you have the second order approximation by considering 3 terms. This is the simplification after using calculator, take it to the left hand side, you will get the absolute error to be like this. Similarly, the successive approximations, that is third order approximation, 4th order, 5th order, 6th order, 7th order of the function sine pi by 3 can be calculated, and their absolute errors can also be calculated in the same way, and they can be tabulated. If you tabulate those values, you will see the table something like this. Already we have seen at 0th approximation, this is the value of the function, and the error is this much. The first approximation, the value of the function is this thing, error is this thing, and similarly you go on doing. At the 7th order approximation, the value is this much, and you see the error is 0.00000077. So what we are concluding here, when we consider the approximation of higher order, the errors will be lowered. That is, if you retain more and more number of terms in the Taylor series expansion, then the error will be reducing to a greater extent. So the value obtained will be very much closer to the exact value. So this is the conclusion from this table. Now this completes the solution of that second question, and you please try this example by yourself. This is to be done in a very similar way as that of the second example. Please do it by yourself. And now with this I will conclude. Again, you can refer this book for your problem solution and exercise questions. And with this, let me stop this lecture. Thank you one and all for watching this video.